Resisted motion then. Let's look at resisted motion. As we said, resistance is always in the opposite direction to which you're travelling. So, Newton's third law. Basically, there's three cases. So case one, we're moving in a horizontal line. And if that's the case, let's say I'm travelling to the right. So that's going to be my resultant to the right, which means I've got resistance to the left, and that's pretty much it. Might be friction, could be anything. Could be air resistance, could be swimming through the water, whatever. I'd end up with something like this, but from a differential equation. Mass times acceleration would equal minus whatever r is, divide through by m, and that would create something to solve. Second case is maybe we're travelling up. We're going up. Now, if that's the case, my resultant I'll put up, direction I'm travelling. I would have the force due to gravity down, mg, or weight, and there would be a resistive force as well. So when I set it up, it'll be minus mg minus r, because they're in the opposite direction, divide through by m, and we'd solve that. It doesn't change the fact that the greatest height is still going to happen when velocity is equal to 0. I mean, that doesn't change. Downwards motion. But now I'll define the resultant force going down, direction in which I'm travelling. We've still got the force due to gravity, resistance in the opposite direction. So it means when we set it up, now the mg is positive because it's in the same direction that I'm travelling. So I'll get mg minus r, divide through by m, and I'd work with that. With downwards motion, we have this thing called terminal velocity. That's basically when the resistance and the force due to gravity balance out. Happens when the acceleration is equal to 0. Okay, let's look at some questions. So the first year of the new HSC course we're doing now, they asked this. A 50 kilogram box initially at rest, box is being pulled along the ground, force of 200 newtons, but it's at some angle of 30 degrees there. Experiences a resistive force of 0.3 r. R is the normal force. And that's what I was saying, that friction tends to be some multiple of the contact force, so normal force. By resolving the forces vertically, so they've told us to just look at the vertical forces, show that that contact force, R, turns out to be 400. So here's my diagram. I'm just interested in vertical forces. So I've got to break that force that they were pulling it with, which is at an angle, break it into its components. So it would go to the right and then up. Well, I suppose you could go up and then to the right, you end up in the same spot, I suppose. There's Bob. Let's put all the vertical forces in. We have 50g going down. We have R, the contact force, going up. But we now have the component. So it's going to be 200 times sine, because it's opposite to the 30 degrees. So 200 sine 30. Now, all the vertical forces, however, I know sum to be 0. It's not like the box is jumping off the ground, it's on the ground. So R plus the 200 sine 30 minus the 50g, it's in the opposite direction. All of those must sum to give 0. That allows us to find R. So substituting in sine 30 is, of course, a half. G, did they tell us to take 10 for G in the question? They must have. Ah, there you go. Take the acceleration due to gravity to be 10. Makes the maths nice, I suppose, even if it is a little inaccurate. So R is 400. Okay. Now they want us to look at the horizontal forces and show that horizontally it's basically 53.2 newtons. Now we shall draw the horizontal forces. So the resultant force, by the way, I've put it in blue, a different colour. You don't actually draw the resultant force on your force diagram. It's not a force. It's the result of all the other forces. 200 cos 30 going to the right, 0.3 r going to the left. So the resultant force is 200 cos 30 minus 0.3 r. Oh, they've used the term net force. Net force, resultant force, essentially the same thing. Yeah, that works out to be 53.2. Then they want us to find the velocity of the box after the first 3 seconds. Okay, resultant force we now know is 53.2. The mass was 50, so I know d to t is this constant number. Well, I suppose I don't need to use integration because it's a constant, but I will anyway. Separate the variables. 0 to v and 0 to 3. Bingo, there it is. 133 125 times 3. 3.2 meters per second would be our velocity. You realise I could have just, it's like using speed equals distance over time, but the next level down, I could have said acceleration is velocity over time. Particle projected vertically upwards, velocity of u in a resisting medium. Assume that the retardation due to this resistance. So we're going up. So my resultant force, again, if I was doing this in an assessment, I wouldn't be writing the resultant force on there. But resultant force is up, mx double dot. Down we've got mg. The resistive force is kv squared, so retardation tends to be resistive force. I know down there at the ground, x equals 0, v is equal to u. That's information they've given me. Okay, set up my differential equation. Divide through by the mass. Interestingly, I should have just left that as one fraction when you think about it, because I'm going to have to rewrite it as one fraction anyway for the integral. Separate my variables, and there we have it. So we know that when x is 0, velocity is u. We want to find x when velocity is 0. Subbing in, log of mg plus kv squared. What a lovely expression. Now this is more fun than using numbers, isn't it? Just use pronumerals, that looks much nicer. M on 2k, the log of 1 plus ku squared on mg. There's my greatest height. Notice I haven't got an absolute value on this one. Why? Well, u squared's got to be positive, g of course is positive, mass is positive, and my constant's positive as well. So, I mean, how do I know the constant's positive? Well, if the constant wasn't positive, then that wouldn't be in that direction, because it would be going up instead of that. So, hey, you can leave the absolute value in there, it doesn't really matter. But there was no need for it on that one. But we still haven't finished the question, because we now need to find the time it takes to get there. So now I will say acceleration is dv to t. We get a slightly different thing to integrate. Now we get some inverse trig. And look at the a squared on this, mg on k. So don't forget your 1 on a out the front there. So we've got the square root of k on mg, which is also multiplied by m on k. Inverse tan of root k on mgv. Substituting in, thank goodness the inverse tan of 0 is 0, makes it a little bit nicer. But there's the time in all its glory. It takes root m on kg inverse tan of root k on mgu seconds. Oh, the physics teachers would be squirming right now. How could you write an answer like that? Let's do one where we're dropping a body. Body mass 5 kilos, drop from a height. Air resistance is proportional to the speed v. The constant of proportion is 1/8. Find the velocity after time t. Down we go. M, but they've told me mass is 5, so I've written it as 5 times acceleration for my resultant force. I've got mg, 5g in this case, and going up, 1/8 of v. So the air resistance is a force. They've told me the constant is 1/8. Let's set up our equation. We end up with acceleration is g minus 1/40th of v. We want to link velocity and time together, so we'll make it dv to t. Again, right law was one fraction, because we've got to separate those variables out. Oh yeah, that's just a log function. So log function, sub in, and there is 40 log 40g on 40g minus v. But we want v as a function of t, not t as a function of v, even though it does rhyme. T on 40 is the log of that, so exponentialise both sides. I think I'll turn that upside down, so now it's e to the minus t on 40. Play around with it, and eventually we get our velocity equation. What would the terminal velocity be? Well, now with the information I've actually got a couple of ways I could work out terminal velocity. First way is to simply say, well, I know what happens when acceleration is equal to 0. And therefore, v is 40g when we sub into the acceleration equation. Of course, the other thing I could use now is my velocity equation, because terminal velocity is the same as limiting velocity. So, limit as t approaches infinity. I've got a backwards exponential there. I know as t approaches infinity, that will approach 0. So this velocity will approach 40g. Either way, it doesn't really matter, because it's the answer we're after. But there's our terminal velocity, 40g. How far has it fallen after t seconds? Well, velocity is dx to t. So let's play with that equation. Separate the variables, integrate, substitute in, There it is. Displacement is 40 gt plus 1600 ge to the power of minus t on 40 minus 1600 g. Let's go back to an actual HSC question. First year again, so they had a couple of these sort of questions in that particular paper. This one was a beautiful pulley question. So the two masses are at rest. This is not how you don't use your physics. Don't use your physics ideas here. The two masses are at rest before being released. So here they are. We have to show that dV to t is this expression. So unless they gave it to you, so if you couldn't get it, you could use it in further parts. There's two different masses. Let's look at the forces happening on the two masses. On the left mass, we have the force due to gravity, but its mass was 2m, so we've got 2mg. kV going down, because in our, let's go back to the original picture, in our system, you'll notice the arrow on the larger block, but it's kind of logical when you think about it. If you've got two things on a pulley, well, the heavier one's going to pull the lighter one up. So the lighter mass is going up, therefore its resistance is going down. So kV, and they're attached by this string, so there's going to be tension in the string. Resultant force vertically would be 2mx double dot is t minus 2mg minus kV. Now if we look at the right hand side, that mass has got 4mg, the force due to gravity. Its resistance though will be going up because it's going down, opposite direction. Tension is going up with this one as well, and it's got to be the same tension because it's the same string. So basically it's the tension that links these two systems together. So 4mx double dot is 4mg minus t minus kV. I'll make t the subject on the left hand side, substitute it into the right hand side, and I can come up with a differential equation. There it is. Acceleration is mg minus kv on 3m, which is what they've asked me to find. Wow, they said dV to t, but dV to t is of course acceleration. Given that the velocity is less than gm, oh well, I suppose they like alphabetical order. It's unusual to see it as gm, it's mg normally, but gm over k show that when time is 3m over 2 log 2, the velocity of the larger mass is gm on 2k. Well, dV to t, that's what we know. Separate out my variables. It's not a nice number I'm substituting in, but that's what it is. 3m on k log 2. Integrate. It's a log function. I have got an absolute value this time, you'll notice. Log of mg minus kv, sub in. Now, what are we trying to find again? But hang on a sec. They told me velocity was less than gm on k. Well, if that's true, that thing that I'm finding there I know is positive, the mg on mg minus kv. No way I could get a negative number there. I guess what I'm saying is I don't need the absolute values. Therefore, I can just say mg on mg minus kv must be 2. It's not going to be negative 2. Solving that, we get v is mg on 2k. The next year, object of mass 5 kilos on a slope, inclined at an angle, force due to gravity, two forces, and so on. Well, let's draw a picture to solve this. They want us to find the resultant force. It's going to be this. But notice they say resultant force down the slope. That's what they're interested in. So there it is, sitting on some sort of ramp. Force due to gravity is still going to be going down. So that's 5g. Going up, we have a resistive force. It's going to be 2v plus 2v squared. See, they say two forces, one of magnitude 2v and one of magnitude 2v squared. I've just combined it into one thing and say, oh, well, these two become this force going up the slope, they said. Must be the resistive force, maybe it's friction, something like that, because the object's travelling down, so it's going in the opposite direction. There would be a normal contact force at right angles to our slope. Okay, so there is our force diagram. There are all the forces. They want the resultant force down the slope. So that's the direction I'm interested in. Well, in that case, I'm going to break gravity up into those two components. 60 degrees would work out to be there when you play around with the geometry of it. So if I just look down the plane, the mx double dot, the resultant force, would be, well, 5g sine, because it's opposite the 60 degrees, that's in the same direction, so that's positive. The 2v and the 2v squared are in the opposite direction, so that'll be minus. Sine 60 is root 3 on 2. Yeah, so we get what they're looking for. That's what they wanted. There's one value of v such that the object will slide down the slope at a constant speed. Find that value. Well, if it's sliding at a constant speed, the acceleration must be 0. Therefore, the resultant force is 0. So essentially, we're just solving this equation. It's a quadratic. Quadratics usually produce 2 solutions. And they're asking us they're telling us there's only one. Well, why is that? Well, because v's got to be positive. Because if that value was negative, then it would be travelling in the other direction. We know it's only going in one direction. And that is our positive answer. The square root of 4 plus 2 root 3 over negative 4. But they did say to 1 decimal place. So subbing it in, we get 4.2. Okay. So 6D and 6E.